So I'm Patrice Aknin from SystemX, and I am happy to introduce you this sequence about scientific challenges and contents for the program Confiance.ai. It is not a very simple exercise because the program is very large and the program is very large and rich, and the people who were here yesterday, I think have already realized this. At the start of Confiance.ai, a lot of work was carried out by the partners to structure the architecture of the program in 7 projects, and I remind you of them here on the slide. 7 projects, and the logic of the program architecture was to set the development of work intended for industrial engineering by proposing tool-based processes for the development of trustworthy AI. So very quickly, it became necessary to take a step aside to look at what were the upstream scientific challenges useful to the program, and what is some open research questions. And identify these challenges and propose them to the academic community. So the list of identified challenges is very long, and for clarity and legibility, we have grouped them into 3 categories. 3 categories you can see on the slide at the last part of the slide. So for data issues, we have a group of challenges. The link to humans seems to be a very important part also. And the last one, and not the least, system aspect of trust in AI. The 3 categories have the same importance for me, and there is no prioritization between them. So for the first one, the data issues, we distinguish 3 families of challenges: build data, qualify data, and more global issues about the data management. And for each of them, it's obviously the trust dimension that is questioned. I won't have time to detail each of these points, there is too much, but I will extract a few. For example, for build data, the integrating of different sources of information, physical information, simulation, and knowledge also, called data augmentation, is a very important way to take advantage of each kind of data in order to keep trust in them. Domain adaptation is a very well-known field associated with machine learning and transfer learning. This scenario arises when we aim at learning from a source's data distribution as a well-performing model on a different but related target data distribution. This is a good solution to constitute large training data set. In a world where the labeled data are often rare and expensive, solutions to supervise annotation phase and assess coverage are very useful. Active learning is one of them, and we put it on the challenge. The qualified data also, qualified data, once the data set has been created, its qualification is essential. This qualification is a large part of the work to do in order to evaluate AI chain. This is because the data contains information or does not contain information. And finally, because the quality of the machine learning model is largely a reflection of the quality of the data used to learn it. You find here measure of representativeness of the data, the problem of bias, obviously, the coverage assessing and the operational domain, problem of the variability of the operational domain, and so on. And the last part, it's about global approach, address the engineering dimension of data, such as data cycle management. We have already heard about this. The second category groups the challenge about the human interaction between user and system, mono interaction or multi-interaction. Very important concepts such as explainability and acceptability are addressed in this category. These challenges are unfortunately often only addressed during the feedback phase on the use of AI system. I think that the good idea is obviously to address these challenges before the conception of AI system and not after. In this sense, it is essential to have a dialogue between designer and certifier. This is the last part of the challenge of this category. The third part, it's about system aspect of trust in AI. First, how to build AI components with controlled, trustable performance. The formal approach is the Graal, but today there is a lot of work to do in order to expect the formal demonstration of safety of AI. We have after this sequence, we have a presentation about this subject. It is certainly the most upstream subject. The second family of subject concerns the qualification of AI-based components and systems. How qualify the behavior of such a system, how measuring the outlier's response, all of this with a variable context. This part of challenges greatly feeds into batch 1, so these first years of the Confiance.ai program. The third family of challenge concern also embedding AI, which are all specificities such as real-time constraints, energy performances, hardware architecture compatibility. More than this subject, there are also the principal problem of guarantee the conformity of the embedded model with the development model. And the last part of challenges concerns the truth and AI by system engineering in the system point of view. And you can see here some challenge in the last part, global approach. I have no time it's a flyover all these challenges. I have no time to detail it, but we can discuss after the talk, obviously. Now I give the floor to Georges for explanations about how this scientific roadmap has been shared with the academic community and what are the results of this sharing.
So good morning, everybody. Good morning, everybody. Can you hear me? Is it okay? Okay. So we had this dream of all challenges which should be solved in this program. And so now we have to come back to reality. And I'm going to present you the results. So we launched a call for interest among the academic community to try to find solutions to these challenges. So we addressed French laboratories and especially around the two IRTs in Saclay and Toulouse. There were three possible ways to contribute from just like subcontracting a small study or a state-of-the-art from the lab, then some maturation of the scientific work with a postdoc tool, and finally a more basic research or of course applied research with PhD students. So we had 32 responses, proposals, and we selected 12 of them. You have the agenda. So I'm going to describe briefly the different selected projects. We had 9 with PhDs, 4 with postdocs, and 2 studies. As for the process, each project, each proposal was selected by the validation of one project in the program. So you had the list of the projects, which is decomposed, the program is decomposed in 7 projects. So each topic is associated to one project. So as for the characterization and qualification of AI-based systems, we had 2 PhDs, which are described here. I'm not going to describe everything. One is about using optimization for finding, evaluating robustness, and the other one is more on the operation part of the models, monitoring the models. Then we had 2 proposals, selected proposals about building trustworthy components. One with systems able to be protected against patch adversarial examples on images, and one about building a robust reinforcement learning. As for the data part, so acting on data to provide safe systems, robust systems, we selected 2 PhDs. One about finding extreme examples to be able to find extreme cases where the system should be, on which the system should be trained as well. And another one about robustness and fairness, so more the ethical issues and bias identification. Finally, we selected 3 projects about the embedded AI. So it's the idea of having safe and guarantees on execution time when we embed in real system the different models. So as for the 4 postdocs, again, they were validated by the different projects. Regarding characterization, actually we have a postdoc which is close to the PhD study with Litis in Safran, but we have another topic which was not covered by the previous PhDs, which is about building explanations using some knowledge, symbolic approach to AI-based components. Then we have another approach, which is trying to find a hybrid solution for between machine learning and control theory, which is in Lille Crystal Lab. And finally, the last postdoc is again on the same topic as having temporarily predictable performance when the machine learning scoring algorithms are embedded in real systems. So as you have seen in the different tables, almost all PhDs are now found. So we have students, and they are beginning a bit before the end of the year. Finally, we had 2 scientific contributions, small studies. One is, and I will see that it's the only one which is clearly related to the human part of AI systems, which is about building a platform for being able to do what they call autopsy of a case when there were a failure or incident on machine learning, using a machine learning algorithm. So I think it's a very important point, and there will be a study on this topic. And finally, another study is related to one PhD already selected with Anity Toulouse free AI organization. So as for wrap-up and summary of the result of this call for interest, we can see that the most covered topic is about building trustable AI-based systems with 7 PhDs and 4 postdocs. So this is the most popular topic. There are 3 contributions to the part data, selecting and acting on data to have good components, AI-based component. And what is very, I think it's a pity that we have only one contribution about trustable systems related to human interaction. And I think we should, in the second part of the project, we should try to have more contribution and to suggest more contribution on this topic. So I'm going to ask now Frédéric to go deeper into the different challenges.
So good morning, I'm Frédéric Jurie from Safran, and I'm very happy to be with you this morning. So basically what I'm going to do in the next few minutes is to try to address one of the questions that has been asked a few minutes before, which is what is the readiness of the technologies we currently have? Which is quite an interesting and difficult question, and I don't want to spoil my take-home message, but my take-home message will be that it's actually very difficult to assess the current readiness of the technology. I'm going to explain why. First of all, may I remind that making trustworthy system is a very difficult task. I'm sure that we all agree on that. And so there are different ways to attack it. One way is to start from the specifications, the challenges that have been presented earlier in the presentation, which is necessary, and we have to break it into smaller and smaller blocks until they become easier to define, to evaluate, to find metrics, etc. But on the other hand, we also have to pay attention to the technologies that are actually usable, because otherwise we'll have a practical problem. And so during the first year of the project, well, and I'm sure that we'll have to go forth and back between these 2 steps, refining the requirements and understanding better the technology and try to find how both can match. And during the project, we have been working a lot on the state-of-the-art technologies, and 10 state-of-the-art reports have been produced. I read all of them, and I really encourage you to do so, because they are very interesting and they contain a lot of interesting information. And So what we could hope to find is such document, and you will see that it's not the case, is a list of technologies and the feeling that we have just to pick this technology off the shelf and put it in our systems and everything will be done. Well, actually, it's not the case. So I'm going to take these documents one by one, but for some of them I will be very schematic because I'm lacking of time. This is an exercise that I can do later on with more details, I think. Here I will be very schematic, as I said, because we are lacking of time. But basically there are three types of technologies. Those related to questions that are pretty simple and for which we definitely have answers. So this is the easiest case, but it's only for the few of them. There are also a few for which it's very difficult questions and we don't have any answers. So I think it's an easy situation. It's a bad situation, but it's easy too. And the most complex one for the vast majority of the topics, we have a lot of tools, technologies, solutions, but none of them is perfectly fulfilling the requirements. And it's a bit more tricky because then we have to understand what this technology can do and not do in detail. Let's take. So I have 10 slides. I will skip most of them, but let's start by the first one, which is quite interesting. It's about the technology for runtime monitoring. So basically, the idea is to prevent and to compensate for failure of the system by observing it from outside. So, for instance, if you try to use a system by giving it data that are very different from what it's expecting, it's not going to work, and it's better to detect it before asking it to make predictions. Or if the camera is unplugged and you are sending black images to your pedestrian detector, it's better that the pedestrian detector knows that these are black images. So it's basically these technologies that are addressed by monitoring. So this I took it from the related state-of-the-art document. So in the state-of-the-art document, there are 4 main branches. This is interesting. Why 4 branches? And if you look at them, they are bringing very different by nature, very different types of solutions. For instance, let's pick the second one, which is the tools for predicting out-of-distribution samples. So, well, the idea is to ask the system not to process examples that are too different from the training samples. The other one is related to technologies for uncertainty prediction. So it's very different. The system is supposed to be able to give the confidence it has in its output. Both address the question of monitoring, but in very different ways. So it's important to understand what is the impact of these differences on the trustworthiness of the system. In which situations should we use this or this branch of approach? And then if you look more carefully within one of these branches, let's say uncertainty prediction, then here again you have a lot of methods. And I only picked the most silent ones. There are much more. And I would ask you the question, is it better to use Bayesian networks, or is it better to use Monte Carlo dropout? Well, in fact, they have different properties. Bayesian networks are going to give you formal properties of what you can expect, but they cannot scale to big networks, and they are much more time-consuming. Monte Carlo dropout, it's more empirical, so you don't have any guarantee, but it's faster, and in most of the time, it's working. So as you can see, even within a single branch, uncertainty prediction, we have several tools, and they have different properties. And if we don't know in details what are these properties, it's very, and in addition to the fact that none of them is working perfectly, then we have to know the details if we want to make robust systems. Okay, So let's go to the second type of technologies or requirement, which is the formal verification for robustness. So here again, we are in the same situation. It's a very, very difficult problem. We have a lot of branches, which are each line of each row of this slide present a different branch, and then you have again many methods. They do not scale the same way. They do not give the same properties, and so they are addressing very specific types of robustness. So I have a lot of things to say about this, but as I said, we don't have time, so I'm just keeping the main messages. We have and it's interesting if you look at so maybe I can make one comment on this slide. The topic of explainability, if you look at the state-of-the-art report, in fact, it's not a state-of-the-art, it's a meta state-of-the-art. It's an analysis of almost 10 different state-of-the-arts already published, and we see that it's a very difficult question. The definition of what is expected is not very clear. What is an explanation is not clear either. Yesterday we saw that during the first batch we'll have visualization methods. Visualization methods, they are more giving correlation between input and output and not explanations. So are we happy with correlation, or do we really need to have the causality between the input and the output? All these topics have to be discussed. And here again, there are 1,000 different methods. Is it better to, for instance, for images, as we saw yesterday, is it better to use visualization with the silence map, or is it better to produce counterfactual images? What are the nature of these explanations? Which situations are they made for? I mean, all these things have to be better understood, because it's not clear even in the literature. And then we have also situations in which we have very interesting problems, very practical problems. How can I design my own data set if I have a problem? And actually, the state-of-the-art show that there is no current solution to address this problem. And it's perhaps in part because the academy is not very interested by making its own data set. It might be an explanation, but I fear that there is another explanation, which is that it's very difficult to produce such specifications. And so I think it's a very hard problem for which we don't have, at the moment, any good answers. So we fall in the second category. Let's take this example as an example of the third category, for which, so it's about the characterization of the quality of annotations, which is also very important for giving trust to the person who is designing the system. If the designer can explore its data set, have some statistics about its contents, have more information about the content of the data set, it's something quite important. And at the moment, most of the tools are not very rich with such functionalities, and there is a human in the loop, so it's not very critical, and any help that a system can provide will be useful, and there are methods that are useful. So we are in the easy situation where it's possible to bring, in a very short term, interesting contribution to the designers. I'm skipping the rest, but during the question and answer sessions, I can come up to these topics too. So why is it so difficult to evaluate the readiness of the technology? I'm going to try to convince you and to explain why it's difficult. I'm going to take this simple example, which is the example of out-of-distribution detection, monitoring of system. It's one of the important aspects of the program. And I took as an example a very recent paper. It has been published 3 weeks ago in an ICML workshop. So it's a peer-reviewed paper, and maybe you don't see the title because it's small, but the title is "No True State of the Art?" ? And in fact, the paper, the conclusion of the paper is that the out-of-distribution detection problem is too broad in itself. And depending on the nature of the data, the amount of training data, the backbone you are using, etc., so there are dozens of parameters. The conclusions are very different. So their recommendation is to break it into even smaller pieces and smaller context and do this analysis of performance and readiness in this context. Taking it as a whole is already too complex. And then I will take another example to illustrate the difficulty to evaluate the technological readiness. So I took one of the most famous papers for out-of-distribution detection, which is the Odin paper, ICLR 2018. And as you can see, there is a very big table. That would be much more convenient if I can report the performance of this method with only one figure, like performance is 82%, because then we can compare it to other methods. But no, unfortunately, you need such big tables to assess the performance. And so, as you can see, there are 5 different columns, because there are 5 different criteria that have been used, and they rank the method differently according to these criteria. So, complex problem can be evaluated in different ways, and depending on the way you evaluate it, the performance is not the same. Then, for each big block, you have one method and one data set. And in the second column, and the data set of the first column is the in-distribution data set, and the data set of the second column is the out-of-distribution. And the goal is to detect out-of-distribution images, so the one in the second data set. So you have one row per out-of-distribution data set. Okay, so and if you maybe you don't look, maybe you can read the figures, but if you could read them, you will see that the numbers are very, very different. So it means that from one data set to another, the performance is very different. So you cannot simply take statistics; it's meaningless. And now, if you take, let's say, the first criterion, which is the false positive rate, so the number of false alarms, for a detection rate of 95%. So you expect your monitoring system to be able to detect 95% of the outliers. And then, for this threshold of 95%, you measure the number of false alarms. And if you, well, perhaps you can read them, but I pick them, as I say, they are all different, but if I pick one of the values, and for instance, for one particular data set, you have 30% false positive rate for 95% true positive rate. And then one could ask the question, is it enough to bring trust to a monitoring system? And I'm not sure it's the good question, so I'm not asking it, and I would ask a different question. What can we do with a system having this performance? Because obviously we would like to have 0% false detection, but it's not possible currently, and it's not going to be possible in the next 5 years, I would say. So we have to deal with such systems. So I think the real question is, what can we do with such unperfect systems? And what could be interesting, it's not done in this paper, is to maybe combine this approach with another, or I don't know how, because it's a research topic in itself, but how can we combine such imperfect systems to make a global system which is then, by this combination, more robust, or or a system that can address critical use cases. And I think that we won't be able to answer these questions if we don't go deep enough in the technology and understand very precisely what they are doing, what they are not doing, what properties they are providing, what are the performance in which circumstances, and it's really a huge work. That's my take-home message, and this is concluding this presentation. Thank you.
Thank you to the three of you. So this was, I would say, maybe the frightening part of the show this morning. We have 867 very difficult challenges that we need to address in a bit more than 3 years with 200 people. Very fine. I would like to start with a discussion. So please, if you have comments on what you have seen, I would like you to, yeah, please. We take 2 or 3 minutes for a bit, or if there's a lot of interest, we can just take a bit more, but okay, please.
Thank you for your presentation. I got the message about the need to split the bigger problem into smaller ones. And my question will be quite simple: how to recombine the splitted sub-problems supposedly solved, into the bigger picture?
Well, thank you for the question. It's a very interesting question. Unfortunately, I'm a bit more I'm more a tech guy. I'm developing technologies. I know how they work very well. I'm not a person very good in making systems and combining methods. And I'm sure there are people in the room that are better than me on this topic. So I would like to return the question to the audience. How can we combine such imperfect method in order to produce more robust systems?
So thank you for the non-answer.
No, but maybe you have some answer in the room.
Okay, I have a very simple question. Confiance.ai, we have 45 million euros in 4 years. So how much of all this can we do?
How much?
What percentage of all the challenges that we have in Confiance.ai can we really solve with 45 million euros in 4 years?
It depends. It depends on the efficacy of the consortium. I think that we named many challenges. I think that some of them can be addressed during the 4 years of the program. I'm not sure that all are obviously are. We find results and publish them. It's another question. Perhaps we start with data solution, and the data sets construction is a very important part. I think that we progress on this direction very rapidly. I think that on I'm the conviction that for the data problem, we have split the program, the challenges category in 3 big categories: data and models, and also the interaction with human. My conviction is the data contains information. The models, machine learning models, is agnostic and does not have any information inside. Not so much. So there is a continuum between the data that is the model, I think, and the machine learning algorithm that we use on it. So this, I think that the program have a very good progression to resolve the challenge when we make the bridge between the data part and the machine learning algorithm part.
There is a question by Laurent here.
Laurent Vieille, ANR, Agence nationale de la recherche. Thank you for this very interesting presentation, all of three. I mean, it's a nice counterpoint to the more engineering approach we had yesterday for those who were here yesterday. My question is more, well, it's a bit related to Bertrand's question, is how are you going to progress or to manage as a program? You said, and that the call of interest might have been disappointing in some respect because it doesn't bring the coverture of some aspects. Okay, no, it's well. I mean,
no, it's very good.
Very good. So you are very happy that the scientific studies will solve all of the issues that have been listed this morning. No.
Come on.
Okay. No, it's certainly very interesting. But do you intend to pursue this with the academic community in the next years? I mean, to launch new call for interest, to extend, I mean, from what you had from the SOTAs, more open question, and to launch more academic studies, or are you embarked in a progress in a well? Are you going to extend the work with the academic community?
Yeah, maybe let me answer this. Okay, for the moment, in fact, we have just added a new call for expression of interest for not for academy but for startups and innovative SMEs, and we have had 44 answers, and we are supposed to give the results, in fact, the day after tomorrow. So we will be a bit busy with this in the next weeks and months. And so before launching a new call for interest for the academics, we'll look at what we can do with startups. They also bring a lot of interesting technologies, and they have good research too, I think. So we'll look at what we have globally and see whether we need to go to extend it a bit more. But I think that we will, globally speaking, and when we will collaborate more with our friends from Germany and our friends from Canada, you know that we are also discussing with the friends from Canada, then probably we have we already have a very interesting setting, and I think we have to look at it broadly before launching another wide call for interest for the academic community. But that's just my personal feeling. We'll see what the steering committee decides. Yeah, we take just one more, and then we switch to the... Ah, tu veux commencer?
Non, c'est pas ça. I would like also to make a comment to a previous question. Sorry for being so late. One question was, which part of the program are we going to make during the program? I won't put it this way. I think we have the obligation to use the most advanced technologies, I mean, when we are developing critical systems, even if they are not perfect. If something exists and can bring the trust we have in the system and increase the reliability of the system, it's our obligation to do it. So at the moment, most of the AI system existing do not embed any breaks of trust in it, and so I would say that at least if we know what are the technologies that are existing today, and we know how to take the best of them, it will be a big improvement. I will be very happy with this.
I agree. Just one last question before moving to the next sequence. Yes, please.
I have a question related to the generalization of the solutions that you have. We know that we are living now at an increasing speed. For example, the system that you have built and was very trustworthy on 4G technology for the telecommunication network might not be trustworthy on 5G technology. So how can you deal with this huge amount of variation?
They will think about it.
Well, I think it's why we have to understand exactly what which brick is doing. We cannot just take it as it is without understanding the deepest ways it works.
Yes, I would like to add a more optimistic thing about the discussion. I think one important thing in the program is that we gather several industrial partners which propose use cases, and this is an interesting methodology to follow these use cases and for them at least have a good solution, even if everything seems to be very complicated. We will have some results on the use cases and probably identify some mutualization between these use cases, and this will be a nice win, I think.
Thank you. Let's move to the next sequence. Thank you to you all.
I just want to put another point for the previous question about the quality of the program and how do we think that the result is gone. I think that for the batch 2, the problem of interaction with human is very important, and we have to address this more than we have done now. It's very important to know how the humans build the trust between them, between humans, and to inspire for the construction of AI machine. I think there is a good question on this.
Yeah, I could ask an additional question on that, but I won't, because it's time to move to the next sequence. So please, thank you to the three of you.